Dear viewers, welcome you to the session on characteristics of data structures. Today, we are going to look into the characteristics of data structures, which are fundamental to understanding efficient programming and problem-solving techniques. These characteristics encompasses various aspects that influence the effectiveness and efficiency of the algorithms and programs. So let's explore each of these aspects in detail. The correctness of a data structure refers to its ability to store and manipulate data accurately according to the specified requirements or operations. A correct data structure should perform operations such as insertion, deletion, and retrieval without introducing errors or unexpected behaviors. Ensuring correctness is crucial in developing reliable and robust software systems, such as incorrect data manipulation. Rather, such incorrect data manipulation can lead to logical errors, data corruption, or it might even lead to program crashes. Time complexity. It measures the efficiency of an algorithm in terms of the time it takes to execute as a function of the input size. For data structures, time complexity analysis help us to understand how efficiently various operations can be performed. Operations such as searching, sorting, or traversing elements. A data structure with lower time complexity for essential operations is generally preferred as uh, excuse me, it indicates faster execution and better performance, especially for large data sets or time sensitive applications. Space complexity evaluates the amount of memory required by an algorithm or data structure to solve a problem as a function of the input size. Efficient use of memory is essential for optimizing resource utilization and avoiding memory-related issues such as memory leaks or excessive resource consumption. Data structures with lower space complexity are favorable as they consume less memory and enable efficient utilization of available resources, leading to better scalability and performance. Dynamic memory allocation refers to the process of allocating and deallocating memory dynamically during program execution to accommodate various data storage requirements. Data structures that support dynamic memory allocation, such as trees or linked lists, offer flexibility in managing memory resources and adapting to changing data sizes or structures. Effective management of dynamic memory allocation is very crucial for optimizing memory usage, minimizing memory fragmentation, and ensuring efficient utilization of system resources. In this segment, let's look into static memory allocation, a fundamental concept in programming that involves allocating memory for variables at compile time. Understanding the memory allocation process, addressing of variables, as well as the limitations and constraints associated with static memory allocation is very important for effective programming. Let us look into these a little more detailed. Memory allocation process. A static memory allocation occurs at compile time, where memory is allocated for variables before the program execution begins. In statically allocated memory, the size and location of variables are determined during the compilation phase based on their data types and declarations. Once allocated, the memory remains fixed throughout the program's execution, making it suitable for variables with fixed sizes or lifetimes. In statically allocated memory, each variable is assigned a fixed memory address determined by the compiler. These memory addresses are typically known and fixed at compile time, allowing for direct access to variables without the need for dynamic memory management techniques. Accessing variables using their memory addresses enables efficient and direct manipulation of data, enhancing performance in certain scenarios. In this section, we will look into memory allocation best practices that are aimed at optimizing resource utilization and management in programming. Whether it's dynamic allocation or static allocation or efficient memory management techniques, adopting these practices can enhance performance, scalability, and reliability in software development. Let's look into it in little more details. Effective resource utilization is crucial for optimizing memory usage and minimizing wastage. Memory-intensive applications, in particular, require careful management to ensure efficient utilization of available resources. Best practices for resource utilization include minimizing memory footprint, optimize data structures and algorithms to reduce memory consumption, avoiding unnecessary memory allocations or data duplication, avoiding memory leaks, implement proper memory management practices to prevent memory leaks, such as deallocating dynamically allocated memory when no longer needed, recycling memory, that is, reuse allocated memory whenever possible to minimize overhead and improve overall memory utilization. Recycling memory on rather can involve techniques like object pooling or memory caching. Effective memory management is essential for maintaining program stability, reliability, and performance. Best practices for memory management includes using automatic memory management, utilize programming languages or libraries with built-in memory management features such as garbage collection in languages like Java or C Sharp, proper error handling, that is, implement robust error handling mechanisms to detect and handle memory-related issues, and profile and optimizing, that is, profile memory usage and performance to identify bottlenecks and areas for optimization. Optimize memory-intense operations or data structures to improve overall program efficiency. Dynamic memory allocation allows for flexible memory management during program execution, enabling efficient utilization of memory resources. Best practices for dynamic allocation includes limiting dynamic allocation, like minimizing dynamic memory allocation where possible, as it can lead to fragmentation and overhead. Prefer static allocation or stack allocation for variables with fixed size and lifetimes. Memory pools, that is, implement memory pooling techniques to reduce overhead and fragmented associated with frequent dynamic memory allocations. Memory pools allocate a fixed size block of memory, and reuse it for subsequent allocations, improving performance and reducing overhead. Static memory allocation involves allocating memory for variables at compile time, providing predictable memory usage and performance. Best practices for static allocation includes limiting global variables or minimizing the use of global variables as they remain allocated throughout the program's execution and can lead to namespace pollution and potential conflicts. Const correctness, that is, utilized const correctness to ensure that the variables allocated statically remain immutable when necessary, reducing the risk of unintended modifications and improving code readability and maintainability. So, on the whole, memory allocation best practices focus on optimizing resource utilization, memory management, and allocation techniques to enhance performance, reliability, and scalability in software development. By adopting these practices, programmers can improve program efficiency, reduce memory overhead, and minimize the risk of memory related issues in their application.